Okay, we are recording. So, hi, my name is Chris Rocky. I am the district hydraulic engineer. I have been working for Caltrans for about 24 years. 6 of those years was in design, and the last was at 19 years I've been working in hydraulics, and the past 5 years I've been the supervisor in hydraulics. Um, Before we talk about watersheds, I'm going to take you right to the beginning on what you should do with this system. Um, what I'm going to present to you is a system that I myself have used in a few projects. It's been developed through that 19 years in hydraulics. Um, it's not my, these are not my inventions. These are things that were taught to me from other people, and it has worked nicely for me through the years. This is what I teach all the hydraulic staff or anybody else that comes to ask. And then I should say that there are many different ways to do the calculations that we're going to talk about through these series. And this is not the only method by any means, but it is a nice method to come back to check your other method against. So with that said, let's go ahead and start at the very beginning. And I'm going to go ahead and share now. Watershed delineation and flow calculations. And here are some links that I'm going to talk about throughout the course, and I will make those available to you. And so when you start a project, the first thing you need to know is what drainage systems do you have existing already out in the field? And that is the point of this spreadsheet here. You start with the existing, you go in, you fill in this spreadsheet as much as you can, and then the missing data you can collect when you do field reviews. Um, this is a good opportunity to help you get good and familiar with the project as you are, as if it's a brand new project for you, it gets you a way to get and look at every culvert in the project. So what you want, I'll just go through the list here. The drainage system number, item, and post mile. I'm going to say that these columns are optional and you can tweak them as you need to. The Yeah, so if you don't have some of these items, that's no big deal. You can omit them. And then here's the alignment, and then the location of it. So when you're looking up the alignment, is it on the left or the right hand side of the road, or maybe in the center of the road? And then the offset to that location. And that's just so somebody basically trying to find this in the future will know roughly where to look. The size of the pipe and the type of material the pipe is made out of. In this case, WSP is welded steel pipe. And then the end treatment. The end treatment on the inlet, a head wall, flared end section, maybe no end treatment. In this one here on the top, it happened to be kind of more old-fashioned stacked stone type head wall. And then the outlet as well as the same type of comment. Now the flow line elevation, um, you should be able to get those out of surveys. So you'll need the upstream flow line and a downstream. You'll need to get the length of the pipe from surveys. And then there's a calculation here that's just a check to give you the slope of the system. And then here you will collect this information in the field, the flow line to headwater and the flow line to tailwater. I will talk more about these type of measurements later on when we talk about the hydraulic grade line. This flow line to headwater is what it says. It's a flow line of the culvert to the headwater elevation of concern. And then it gives you the final headwater that you'll use in your calculations for hydraulic grade line. And then in the end here, it'll give you the final tailwater you'll use for your hydraulic grade line calculations. And then a couple of notes on the bottom of how you might have come to a couple of these numbers. Um, I guess I should have started that every project requires a drainage report. The project engineer is responsible for the drainage of the report, is responsible for the drainage on the project. And so most of the time, the project engineer elects to have hydraulics do the work and we do the work for him. But ultimately, in the end, it's up to him to make sure that he's got the calculations and everything necessary for the drainage systems. Um, I know in the project you guys are working on, most of this has probably already been accomplished, so probably won't apply to what you're working on right now. But this is a perfect place to start when you're working on a new project. Now that you've gathered all of this information, this is where I stop on my first discussion with my team. I tell them to go out, get this information, and once you've gathered this information, then we get back together and we'll go to the next topic. That topic is going to, that topic will be the watershed delineation. And the summary of existing culverts is something that we're going to put in the drainage report. It has to be included in the drainage report. So you might as well get started on it early in the project, and you'll have it completed when you need it. And then there's often, with most projects now, the culvert inventory program has already gone out and done a survey and knows where all the culverts are. And they have a KMZ file that's an overlay for Google Earth, and you can tell where all of our culverts are now. And boy, by today, they've probably finished or only have maybe a dozen or so culverts left to do in the district. So it's a pretty complete inventory. They will provide you this list of culverts for your project, and then they will color code them as to the health of the culvert. And then most of the time they will provide some kind of recommendations from their program as to what they think we should do to rehabilitate the culvert. Most of the time these recommendations are made before they actually visit the culvert, and it's just based on the color of this. So we always double check this in the field later. Going across this one is a drainage system number, which is the same as yours, the inspection date of it. The system number is a number that's unique to the culvert inventory program, and that's how they identify that piece of pipe that's under the ground. When you're in communication with that team, they like you to use those numbers so that they know which culvert you're talking about. The type of culvert, circular, the length, the material, the culvert, the diameter, and then width and height, that would be for a box culvert. And then the health score with, I believe the lower the number, the worse the score, the higher the number, the better. And then they use that health score to determine what rehabilitation method that they're going to recommend. Is there an inlet on this culvert, or a no end treatment is NET? And then it gives you the post miles and where to look for it. And then here is their comments: CIPP line to culvert, for example. Here it says remove and replace. This is a good source of information to get this one started. Now that you have this information, then our next step will go to the watersheds. You will end up drawing watersheds, off-site watersheds that look something similar to this. This is very quickly is the outline of the watershed, the soils in that watershed, and the flow line. You can see the flow path through the watershed that we use for the time of concentration calculations. And these will need to be a display in the drainage report as well. And then this will also be displayed on a quad map. You will use the quad map to draw the watershed if it's an off-site watershed. If it's an on-site watershed, it'll be a little bit different. And then here's our on-site watersheds. And I will talk a little bit more about them in detail in a few minutes. Basically, it's just pretty simple. The big deal is to watch where the crown of the road is and decide whether it's flowing away from the crown or across the super, and just track it that way. The next one, we'll go and start talking about how to draw the watershed. I'm going to bring up another drawing here. So what this is just a sketch for you. I have this red culvert drawn in right here, and I have a red culvert drawn in right here. Now I'm going to start with the blue. When I do a watershed, what I always try to do is sketch in where the flow paths are. And I just sketch them in so I can kind of get an idea where the water's flowing. In this case, I can see it's flowing down through here. Now, when we cross the contour line, you always cross the contour line perpendicular. You don't want to cross it at an angle. It's not appropriate, and it shows that you're an amateur. Cross them perpendicular here, here, and then we're off to the culvert. Then you can connect them after you've crossed perpendicular. If you need to change, the top of this one would come through here. And then if you need to change direction, you change direction inside the contour and cross them perpendicular. Here's another flow path through here, crossing these perpendicular. And then this water can flow any direction in between those contours, so that's where you can connect. And then on out, and then it flows on away. And that gives us the flow paths of the water on the watershed. But now we need to know where are the edges of the watershed. So we'll go there next. There's our flow paths. Now the edge of the watershed, what we're going to look for, let's see if the purple, you guys can see that okay. Now right here, there's a ridge that shows us the edge of the watershed right here. So crossing that ridge perpendicular, comes down to right here, filling those in, and then coming up here, crossing that perpendicular, brings this watershed up here. Oh, here's another contour here. And then on up, and it's somewhere up in here is the top of the watershed. Here's another ridge here, cross them perpendicular. And this goes right on down to the highway. And coming up here, it's going to come up this way and across here and then connect. We'll fill these in. And then for this culvert right here, here is our watershed. Then you just have to take a close look at the road to see if the water is running toward the culvert or if it's going to run away from the culvert and on down to the next one. And then to finish this off, we have this path right here with this culvert. So we'll follow the outside edge of the watershed down this ridge, and it comes through here. And it's actually right there. It could be right there. So we will connect these here, come down and connect there. And then here's the watershed and coming across here and then on up to the top. And there we have the watershed for this culvert right here. So the real point that you're looking for is that you're crossing your contours perpendicular and you connect in between, and then watch the slope of the road. Sometimes if it's in a sag, your contours, your watershed will be a little more wide and it will all flow toward the culvert. And then if it's on a grade where the water flows into the culvert or what doesn't go will keep on going, then your watershed will be a little closer to the culvert. And let's see, what else do you need to know here? After you get the watersheds drawn, then what you're going to need to get from them is the area. And you'll want to connect, what I usually do is turn these into a polygon, and I can measure the area in there, and you're looking for the area in acres that you'll use in your calculations later. You want to do a nice clean watershed because you're going to need to show this in the drainage report as a display. And okay, so that's the off-site watersheds. I'm going to go ahead and talk about the on-site watershed now. And I'll remind you that we can come back to any questions you like at the end of the discussion. And here's the on-site watersheds. So the proper way to do an on-site watershed is to get the design contours for the roadway, and then you follow those contours to draw the watershed and the edges using the same methods that I told you in the previous one. But very rarely do you have that kind of information at the time when we're actually doing these kind of drawings. So it has worked out fine for me to just go perpendicular across the alignment and draw basically rectangular type watersheds instead of trying to get them across the contours. And it hasn't been a problem for me, and has allowed me to keep on moving with the calculations. And so just drawing what you're looking for as you draw the watersheds for the on-site is the crown of the road or the super elevation. You'll want to know where it starts to make its changes. And in this case, you can see the flow lines coming down along the side here, and the crown is in the middle, so it's flowing across to the blue line and over. And here it's actually supered. So in this case, it's flowing to the median and over. And then here, as the super continues, it flows across both lanes and then across. And then in this case, the super is changed and now it's crowned in the middle, and the watershed is split in half. One watershed's on the other side and one watershed is on this side. You want to draw one watershed for each drainage inlet, and that would be the open pipe at the end or a drainage inlet of any type. Um, and let's see, what else can I tell you here? Most often on-site watersheds, you'll be using the rational method. And I think that's it. We'll go ahead on to the next one. Now, you've drawn the watersheds, and you know what size you have now of the watershed. We know, where'd it go? Well, pardon me. Well, we know what size the watershed is. We know that it's how big acres it is. And now what we need to do is go into the rational method and do the C equals or Q equals CIA, right? We need the intensity. So to get the intensity, you go to NOAA Atlas 14, and I provided the link to NOAA Atlas 14 for you. And you'll go to NOAA Atlas 14. When you get there, you need to look up two different charts while you're in there. One will be for precipitation, which will be in depth, and you'll see here that it's just in inches, and that's what you'll need for some of the calculations that you may do. And then the other one is in inches per hour. This is the intensity. You're going to need to collect the inches per hour because this is the one you'll use in the rational method and maybe in other types of calculations that you'll use. You need to know which intensity to select. And so you will most likely be using the 5 or 10 minute time of concentration. You calculate the time of concentration for the watershed, and then you select either, you select the longest, either minimum time of concentration of 5 or 10 minutes, or the longer calculated time of concentration. The longer the TC, the smaller the Q. So it's to your advantage to take the time to calculate the TC and find what the longer one is. What I generally do is I start with the biggest watershed that I have and calculate the time of concentration for that watershed. And then I keep going smaller and smaller until the one gets below the minimum acceptable. Now you have on-site watersheds and off-site watersheds. Off-site watersheds, that's the hillsides, that's everything basically off of the pavement. And you generally use the method that I showed you first with the quad map to draw those watersheds. And then for on-site watersheds, you usually use the rational method. And usually the watersheds are small enough that you find yourself using the minimum time of concentration. For on-site watersheds or paved areas, the minimum time of concentration is 5 minutes. For unpaved areas, the minimum time of concentration is 10 minutes. So my recommendation is your first iteration through, just use the appropriate minimum time of concentration, and then you can go ahead and move forward with your calculations. And then once you've got everything done there, Then you can go back and evaluate which watersheds you need to double check the time of concentration for the longer um, the longer TCs or the bigger watersheds. And the big deal with these two spreadsheets is watch out for the inches per hour and the inches. You don't want to mix the two up. It'll mess you up pretty good. And then as you're looking at this chart for the 10-minute time of concentration that you calculate or that you're using, you have different storm events, 2 years, 10 years, 25, 50, 100. For Caltrans, we usually calculate the 2-year storm, the 10, 25, and 100-year storm. The 2-year storm is usually environmental. They're going to ask you for it. They'll ask you for sometimes on some of the permits that they do, and we'll have to provide that to them. The 10-year we use in the hydraulic grade line calculations and in the spread and depth. The 25-year we use in the spread and depth, and then the 100-year we use in the hydraulic grade line calculations. And 5-minute time of concentration for on-site and or paved areas, and that applies the same way. If you're into the minimum 5-minute TC, you're into small watersheds, you probably are going to be using the 5 minutes. And that's going to be about it. Now you've gone to No Atlas 14, you've looked this up. For the current project that you're working on, likely Ray or Chris have already provided this to you to use. So now we'll go on to the rational method. And I'm glad my glasses. Oh, there. Sorry about that. I apologize. I set my glasses on the desk and lost them. So this is the rational method. Rational method is Q equals CIA. Q is the flow, C is the runoff coefficient, I is the intensity, A is the area. However, Caltrans adds a factor of safety to that, which is CF. So it's Q equals CIA times CF if appropriate, and I'll explain a little bit more as we get there. Now, starting with this spreadsheet here, this takes each drainage system one row at a time, or each I guess we'd say watershed or drainage inlet one row at a time. If you have undeveloped area, then you will fill in this area. And in this case, we didn't for the first 3, but for the 4th one, we had 3 acres of undeveloped area. You can go to the Highway Design Manual to find these charts. And in the relief on this one was normal. And the explanation for the normal, high, medium, low is described in where you select that in that figure. And then you select the coefficient that you're going to use for that relief, and then go to the soil infiltration, and it's the same thing. And then the vegetal cover, that's on the surface of the, and then the surface storage. That means water puddles, ponds, anything that's going to hold the water there instead of just let it drain off for you. And so that's where you do the undeveloped if you have the rational method included. Or if you're doing a rational method and you have the undeveloped area included, that's where you add that in. If you're using only the paved area, then you would leave this as 0 or just leave it blank. And then over here in the developed, you have area. We'll put in the area, and then again, what is it? And this is going to be streets, asphaltic, 0.95 is our coefficient we use. And for you guys doing paved areas, you can just copy that. That's what it'll be. And it does a weighted runoff coefficient. It compares the 2 coefficients that you've calculated, and it gives you a weighted number for those. And if in the case down here on the bottom, the runoff coefficient came down to 0.39 as opposed to 0.95. The higher the number, the more water you have running off. And then the next column here is the time of concentration that you're going to use for that watershed. And then we have for the 2-year storm, 10, 25, and 100-year storm, you have the intensity that you've selected. and you've had the runoff coefficient, or excuse me, that's the factor of safety. And so now we have the area, and we have the intensity, we have the factor of safety. The factor of safety for a 2-year storm is only 1. We don't add any extra. For the 10-year storm, it is just 1. We do not add any extra. For the 25-year storm, we add an extra 10%, so it's 1.1. And for the 100-year storm, we actually add an extra 25%, so it's 1.25. So make sure, especially in these bigger ones, you don't overlook this, because 25%, that can make a difference on a pipe size. And then in the end, right here's the magic number you're looking for, the Q for the 100-year storm. The Q is right here, 25-year, and so forth. This is a spreadsheet that I developed to put it all on one page, or all on one sheet. There's another spreadsheet that's floating around that does on one page just one drainage system at a time. That's a nice, easy spreadsheet to follow as well. You don't have to use these spreadsheets. The rational method is very easy to use in a spreadsheet anywhere. So you're welcome to develop your own. Now, to point out one last item here. Why can't I get this? Okay, so CF, C times CF cannot be greater than 1. So we have a C here of 95 times CF of 1. It's just 95, so that's okay, that works. 1 still works. 1.1 still works. For some reason, I can't get any lower on this list. I don't know what's happening here. I don't understand this. Okay, so anyway, my point is the 1.25 times 95, that's probably greater than 1. I have the answers right here, just off the page. And so what you do is you reduce the safety factor down until it's 1 or less. So if you have a say 1.25 is too big, then I would drop it down to a 1.1, see if that works, and then if not, then go down to the 1 and just stick with that. So C times CF cannot be greater than 1, and be sure that you do use the factor of safety. What's our next sheet here? Okay, that's the rational method. So I've talked to you about the rational method. Now, there's 3 methods that we use to calculate the flows. And you use the rational method, technical release 55, or TR55, or the regional regression equation. And those are provided in a highway design manual. The rational method is the go-to one. That's the one that everybody likes to use. That's good for smaller watersheds. It's good for watersheds up to 324 acres, I believe. And then after that, then we move on to TR55. The TR55 rational method starts to kind of get a little off around 200 acres. So between 200 acres and the 300 acres, do both methods, the TR55 and rational method, and use your engineering judgment to select the appropriate flow to use for that system. It's not necessarily the smallest or the biggest. It's after you've done both those calculations as the engineer, which one is the appropriate one to select. TR55, I don't know the max, but it can get up to pretty big watersheds, and that's probably all you'll ever use. If you get into a really big watershed like a river, that's when we'll go to the regional regression equations that are in the highway design manual. We don't use those for designing the culverts and stuff that we use in the highways very often, because they are such a huge watershed. It's usually the bridges. Now with that, you select, I've showed you the rational method. I am going to show the TR55 method in a presentation by itself. And then regional regression, I'm not going to show you that. It's in the Highway Design Manual, and it's a pretty explanatory formula to use. Wow, I think that has finished off everything. So I'm going to open it up for questions, and you guys are welcome to ask about anything we talked about. And I am happy to go back all the way to the beginning if you like. I am providing the links for NOAA Atlas 14, which is where you get the intensities, quad maps, where you can go and get a quad map to use for your draft for the watersheds, and for culvert inventory files that I showed you the spreadsheet. That's where you can go get the KMZ files to put into Google Earth. And then the files that you're going to need in order to prepare the watersheds, the AA and the BB files, the culvert inventory, and a quad map, and an aerial is helpful. There's another program or another website out there called StreamStats, and you can Google StreamStats, StreamStats, all one word. It will automatically draw a watershed, but it is not good enough for engineering level work. You can use it for quick ideas or to double check maybe if you're drawing your watershed and you're not quite sure where you might want to go in a particular area, you can use that one to kind of maybe give you a hint where they would go. But in the times that I've used it, I have found discrepancies in their watersheds 25% of the time. So enough times that I'm not willing to stamp it. So I would recommend that you definitely follow the watershed methods that I'm showing you. And there are other methods out there of developing the watersheds. Just make sure you watch that it is accurate and don't just accept it just because the machine produces it for you. With that, let's go ahead and ask questions. Anybody feel free to raise your hand or go ahead and speak up. Wow, was I that good? Nobody's got any comments or questions?
Hey, Chris, I got one for you.
Sure.
I stepped out for a second, so you may have covered it, but I've had in the past difficulty with getting the quad maps into, say, MicroStation or something of that sort. Is there a process or a streamlined process to make that happen? So that
Those two links that I gave you, that I've provided, you can get quad maps out of there that are geo-referenced, and they should come in right where they're supposed to. And sometimes you just give up. You just there's no other way. You just get the quad map, and you can't get any kind of a world file to get a geo reference. So then what I do is just stretch and warp it and get it up and just do my best to use our surveys as a guide to stretch it into place.
Yeah, I've done that in the past, and it's not the cleanest. So I'll have to use the links you sent.
I would recommend try that link. And then I also have a set of quad maps that have the reference file included with them, but they're a little bit old. So try that link first and see if you can get a current one there.
Hello, Chris. This is Shah.
Hi, Shaw.
Hey, I have a quick question. So regarding the watershed delineation, so there are two different type, offsite and on-site.
Yes, sir.
The offsite one is clear to me. Pick up the contour, cutting the edge vertically. And question for the on-site. So in on-site, when you divide the section of the, can you hear me?
You were okay at first, and then you faded off on me. Go ahead, Shaw.
For the on-site watershed, so when we divide the watershed, that is we are dividing each area, each watershed, targeting to go to a single inlet.
Yes, yes. Every one watershed per inlet. The only exception to that would be is if you had two inlets close together that are essentially acting as one, then one watershed for those.
Okay. Now, what I'm wondering that for the normal standard road condition, so this division we can choose because there is no along the road. We can divide smaller, we can divide bigger as the slope pattern and flow line is pretty much same. So what will be my baseline to decide that how long I should keep the watershed along the road?
So you take the low side of the watershed is your drainage inlet. So the high end of the watershed, that's going to be the crest of the road. So if, pardon me, follow it up until you get to the crest of the highway and then to the top there. So everything from the top will come down to your drainage inlet. Now, if in between the crest and your drainage inlet, there's another drainage inlet, then you'll need to know how much that one intercepts and if there's any bypass coming onto yours. So that you'll need that. That's where you set up your watersheds.
No, say longitudinally, when I follow from the standard pattern of the from the roadway, so the crown is at the center of the road lane, and at the edge towards the curbs, that is the flow is coming towards. So that is understood, but longitudinally, how long I should take to make the length of the watershed to cover in one single inlet? Is there any law or any
Let me see if
idea?
I can. I'm going to share this display again. See if I can make sure I understand this. Here it is. So in this side right here, it's crowned in the middle, and so half of it flows this way and then on down, right? And
Right.
this watershed is flowing from across here to a median island, and then it comes down. So what has happened is this is the high end of it because there's a drainage inlet right here for above it. So anything that gets to this drainage inlet is intercepted. So just this area right here goes to this inlet. Anything before that would go to this inlet right here. And the same would happen. It's a little more clear at this spot. You can see it comes down around, gets to this inlet, and then everything is intercepted. So then the watershed starts over and it goes down to the next inlet.
Okay, so so this is a like a super section. So, but if it is a section, sorry, go ahead.
Okay, you are drafting, you're trying to basically delineate the paved areas. So
Right.
edge of pavement, I guess you would want to go to the edge of pavement.
But how long it should be the in a not in a super section, say the straight section of the road, which is just crown at the middle
Okay.
and a little bit slope. So how long will be the each watershed I will consider? Is there any something to follow or it is just a judgment?
Well, I'm not sure I understand the question, Shaw. I apologize. It for the length of the watershed, when you say length of watershed, I'm thinking this distance across here.
Yes,
And
yes.
so the length of the watershed is determined by what's contributing to it. And since everything on the upstream of this is caught by this drainage inlet, it's only the area that contributes to this inlet.
Okay,
Okay.
okay.
The only other kind of gray area would be is if you didn't have a drainage inlet here, and this would come down and contribute to it, and you'd have to look for where's the high part on the highway, the crest of the highway, And at that point, the water would flow from the crest down this way and in the other direction. So it's either the crest of the highway or the next upstream drainage inlet.
Okay, I got it.
Okay, and I would say as you practice this, if you would like to talk more about it, feel free to ask. Okay, Shaw?
Okay, and I have another question on runoff calculation.
Okay,
So if you please go back to, yes, this is the sheet. So here at the column of time of concentration
okay,
on the DS1A, you considered 10 minute. In the next line, you considered 5 minute. And on the third, you considered 10 minute. So all these three, there is nothing undeveloped. All are developed. All are asphaltic. All weighted coefficient is 0.95. So what make you this difference 10, 5
well,
minutes?
you caught me in that I didn't want you guys to see all of this up here, and what I did is I deleted it so that for today's demonstration, I only had one row of that. So basically there was more up here that I just deleted for today's discussion, and I should have changed that to a 5. You're right. Yeah, that's actually yeah that's exactly what happened because this spreadsheet actually was I don't know 15 or 20 drainage systems long, and I just cut it down for this demonstration. And I guess I can add that attached to this meeting invitation are the spreadsheets that I've shown you, and also the links. So you guys are welcome to copy those and use them. When we talk about TR55, that's when we talk about how to calculate the time of concentration. So if you guys decide that we need to get into the time of concentration calculations sooner, just let me know, and I can talk to you about that. That's a process on its own. So we'll only get there if we have to.
Okay, thank you.
Okay.
My last question on the same sheet, sorry.
Oh,
I have another on the runoff calculation sheet.
okay.
So could you please go back to that spreadsheet? Okay, in 100 years storm, so there is one coming the CF 1.25. And you mentioned that if it is more than 1, so we can
Yeah, so what happened here was 1.25 times the C. Where is the C? 0.95. That can't be greater than 1. And so down here when they were, I need to get those solutions up. I need to get those solutions. I don't know why they're not showing, and I can't bring them up. No. Excuse me just a minute. I'm going to open the actual spreadsheet.
sure. In that the Excel sheet you forwarded, it is the same actually.
Yeah, it's the same one. See, these numbers right here, for some reason, weren't showing up on that spreadsheet that I was just, or that PDF I was just showing you guys. But basically, what it's doing is it's taking the CF here and multiplying it times the weighted coefficient, and and then it double checks these to make sure that it's not too big. And in this case, 1.25 is too big. So we would have to reduce that down until we're at a 1 or less. And in this case, 1.1 brought us right to 1. So if we'd have tried 1.25, it'd have probably been too big.
Okay, so this is just randomly reducing the factor of safety to keep it equal or less than 1. That is the
Yep.
only thing, right? Okay.
Yeah. You just reduce that down to your 1 or less. And I apologize in that yesterday I just took a bigger spreadsheet and clipped it down to this. So this is not the actual numbers that I used for this project. So don't take it as perfect. But the formulas, they're there. And when you put your information in there, it'll give you the right answers.
Okay, thank you. Thank you, Chris. I got it.
Okay, I'll go ahead and stop and see if there's anybody else. Shaw, anybody? I don't see any other hands. Okay. And so the next one after this is going to be the spread and depth on the shoulders. And so that's how it's spread from the flow line over to the edge of travel way, and then the depth of the flow to make sure it doesn't overtop the dike. And then in addition to that, we'll talk about ditches and channels because it's the same type of calculation. I'm going to do that next week, and I'm going to get the video posted on this one as quickly as I can. Let me see, what else can I tell you? I think that's about it. I'd like to say thank you guys for coming. I hope it was helpful.
Thank you, Chris.
Thank you, Chris. Much appreciated.